The Sunrise team welcomes you to another video that is part of a series which explains the results of the use cases that demonstrate the successful application of the Sunrise Safety Assurance Framework. This use case focuses on the testing and safety validation of various components within the perception layer, specifically when the operational design domain of the automated driving system encompasses complex urban intersections and adverse weather conditions. This use case covered 4 of the safety assurance blocks. The query and concretize block was used to define parameters, parameter ranges, and perform scenario sampling and concretization. In the allocation block, the test case requirements were compared with the test instance capabilities. The next step was to execute the allocated test cases, virtual and on proving ground, using individual simulation frameworks and AD functions per partner. Finally, the results were then processed and compared to the evaluation criteria. This use case consists of several partners who have used different systems under test. The scenarios represent various urban situations such as intersections, roundabouts, and parking. Several simulation frameworks and a proving ground were available for the test execution. This use case illustrates the safety test case by building safety evidence through microscopic evaluation on individual scenarios using binary pass-fail criteria. For the safety argumentation, test scenario allocation, co-simulation framework execution, coverage-oriented testing including SOTF analysis, risk-oriented testing including high-risk and boundary scenarios identification, and knowledge-based scenarios are considered. This video shows several demos of different partners. In this first demo, the tests were conducted in simulation due to the lack of real-world testing grounds. Thus, combining real and virtual tests wasn't possible. However, the camera setup fully complies with the SAF specifications. A photorealistic renderer simulates real-world camera behavior. All requirements related to the perception system and ODD were verified using the simulation framework. This case demonstrates an emergency braking event. The top shows the driving view using an external camera. Detected objects by the perception system from onboard cameras appear at the bottom. Using the simulator, multiple variations of this scenario have been generated to be tested, changing scene areas, object positions, and occlusions. Using the capability to generate difficult cases, adverse weather conditions like fog and heavy rain were simulated to test performance under poor visibility. Lastly, to understand the capacity of the driving system, the same scenarios have been generated, varying pedestrian distances and speeds to assess system responsiveness. The test evaluation is based on 2 complementary approaches. First, driving performance evaluation, where collision events are monitored and timeouts are measured to ensure that the driving model executes the appropriate maneuver on time. Lastly, perception performance evaluation, where the detection of pedestrians is assessed using standard metrics such as accuracy, recall, and F1 score. Infineon uses a knowledge-based approach to create test cases. These test cases are based on Euro NCAP scenarios, which are based on expert knowledge and represent an important aspect to consider for supporting ADS validation. This approach enables Infineon to demonstrate the capability of handling knowledge-driven scenarios as well, addressing the needs of many vehicle safety bodies, especially for urban-based environments. Furthermore, this approach actively supports the validation of the safety assurance framework. Since Infineon uses only virtual testing in this use case, the allocation process will not be used to distribute test cases between different test instances, but to verify that a test case can be allocated to the available test instance. Furthermore, since Infineon uses knowledge-driven scenarios, this enables the demonstration that the allocation block of the SAF can handle these types of scenarios as well. Infineon utilizes a demonstration instance to simulate the Euro NCAP scenarios, which highlights the impact of several critical sensor effects and phenomena on the performance of ADS-equipped vehicles. These effects are 1. Phase noise, causing random fluctuations in the radar signal. 2. Interference from other radar sensors, a significant issue in complex urban environments. 3. Mixer nonlinearity, which causes of spurious signals that can interfere with the radar's ability to accurately detect and track targets. And 4. Finally, phase drift, causing the radar signal to become desynchronized. Infineon uses the allocated Euro NCAP scenarios, executed on the virtual testing setup, to determine pass/fail on microscopic level, as part of the overall safety argument. The pass-fail criteria is collision, no collision. The videos show the difference between the implemented sensor models with the sensor effects and a simplified sensor model. In case of the simple model, a collision occurs. Hence, small changes at the perception layer cause huge differences on ADS level. The SOTF standard, safety of the intended functionality, emphasizes the importance of addressing both known and unknown unsafe scenarios. First, let's consider the known unsafe scenarios. The safety assurance framework has been established using Siemens SimCenter Prescan and HEADS software. This framework begins with a logical scenario and, by varying scenario parameters such as speed and operational design domain parameters like weather and lighting conditions through optimization techniques, it generates critical cases that reveal potential safety issues. This systematic approach ensures that known risks are thoroughly analyzed and mitigated. Next, the focus is on the SOTF unknown unsafe scenarios. In this phase, real-world data from intersections is imported to extract actual road users' behaviors. The critical scenario creation optimization algorithm assesses the severity of risks by employing proprietary indicators that measure criticality and novelty. These indicators provide a clear measure of the potential impact of these scenarios. By using novelty and criticality indicators, the critical scenario creation process can uncover previously unknown unsafe scenarios. These scenarios are further categorized using a dissimilarity metric, and the most critical cases are automatically selected for detailed analysis. This comprehensive approach ensures that both known and unknown risks are systematically identified and addressed, enhancing the overall safety of SECOM systems. In the next example, guided search of a logical scenario's safety-critical parameter combinations was used to reduce the overall effort for testing significantly. By constructing an objective function as a numerical representation of relevant metrics like time to collision and inter-object distance, a constrained optimization problem is formulated. A black box optimizer iteratively generates concrete scenarios based on the outcomes of previous simulations. An example scenario with a three-dimensional parameter space illustrates the potential reduction in computation effort in comparison to an open-loop sampling approach, due to the closed-loop method's focus on hazardous cases. This video presents a replay of a right-turn maneuver at a T-junction, simulated using the harmonized V and V framework. It is controlled by the implemented AD function, and its perception sensor's field of view is visualized in red. The ego vehicle wants to turn right. An opponent vehicle approaches the junction from the left, driving straight through. Due to the limited field of view of the ego vehicle sensor, the opponent vehicle is only detected shortly before entering the intersection, which triggers a deceleration of the ego vehicle. Upon completing the turn, the ego vehicle accelerates back to the speed limit using adaptive cruise control. However, since the opponent vehicle is moving at a slower speed, the ego vehicle eventually reduces its speed again to maintain a safe following distance. The last example shows the execute and test evaluation blocks of the SAF. It shows how the AD prototype enters the outdoor parking area. A driver is inside a parked vehicle. This person is opening the door, and the perception system is detecting this new object in its way, braking and stopping the AD prototype consequently. Then the door is closed. This is again detected by the perception system, and the vehicle starts driving again. The test evaluation is passed, as the ego vehicle successfully stops or avoids a collision with the open door. The UC1.1 perception testing in urban environments has been used to validate the safety assurance framework components query and concretize, allocate, execute, and test evaluate partially or fully for urban environments. Limitations resulted from the fact that the partners did not use the same AD function. This meant that not all blocks of the safety assurance framework could be tested, or some only partially, such as the allocate block. This was the demonstration video of UC1.1 urban perception testing. Thanks for watching.